So for the next presentation, we have Dominique Rodriguez, who will be presenting on exploring the potential of a barometer as a transfer standard for infrasound calibration.
Okay, thank you very much for the introduction. So, yeah, I'm Dominique Rodriguez from the LNI, the National Metrology Institute in France. And so today I propose you to present you a study which consists on exploring the potential of a barometer as a transfer standard for infrasound. For infrasound calibration. Sorry. Okay, so our motivation for this work arises, of course, from in the context of the quality assurance for EMS measurement systems. As you know, the EMS is a key tool to enforce the nuclear test ban treaty, and so ensuring data quality is essential, supported by the operational manual, of course, but also by the quality assurance infrastructure as presented just before by Richard. And so, in this context, ensuring the data quality requires accurate and, of course, regularly calibrated instruments. So, the infrasound measurements within the EMS must be traceable to the international system of units, and the metrological traceability, this metrological traceability means different needs at different levels. On the top, we will find the first realization of the unit, the primary reference standard, which is usually established by a national metrology institute. And at lower levels, we will find the accredited labs and expert labs, which require working or traveling standards in order to perform secondary calibration of sensors, usually by comparison against such a working standard. So you have here two examples at Sandia and CEA, but sometimes also on field we need such a standard. You have also in the photo another device developed by CEA, which is a portable calibration system, which requires also such traveling standard to perform this calibration. So this study fits directly into that need to find a reliable working or transfer standard for this purpose. So what resource do we have for this purpose? So traditionally, in acoustics, microphones serve as a transfer standard. They are robust and easy to deploy, but more importantly, they are very well established. We have many ways to calibrate them, many standards also, and of course, they are traceable to primary standards. But the only issue is that probably at lower frequencies, in ultra-low frequencies, their performance are lower because the sensitivities dropped, reaching to quality measurement, poorer quality measurements. We have microbarometers. They cover the full frequency range of interest in infrasound, but they are heavy and bulky, and sometimes it's less practical to implement them in the laboratory. And the barometers also, they are robust also, but the main specification for which we are interested here is that they have the capability to bridge the static and the dynamic domain. So this is why I propose to evaluate now. Okay, so the basic idea is to explore how a barometer with its ability to bridge the static and the dynamic calibration domain can be used as a dual calibration device to establish such a reliable transfer standard. So here we tested a barometer, a Keller PEA 33X, which it uses piezoresistive technology. In the following operating range. One interesting option of this sensor is that we have the possibility to scale, to range its analog interface to a smaller range to fit better to the infrasound operating range. So here, finally, the objective of this operation is to increase the nominal sensitivity, minus 60 dB here, but to be perfectly clear, these do not change anything on the sensitivity part of the transducer. So it's only a gain on the analog interface. So the advantage is somewhat relative, but in any case, it's better. The second point for why we choose this sensor, and probably it's the most important specification for us, is that it is expected to have a flat frequency response up to approximately 20 Hertz, and this is very important for this kind of comparison because this makes the static and dynamic results directly comparable. Okay, so a few words about the calibration method. So we used two calibration methods. The static calibration was performed by my colleagues from the LNE, the Static Pressure Lab in Paris. They used a method by comparison against a reference barometer and by using also a buffer volume to stabilize the steps of static pressures. For the dynamic calibration, I used, they were provided in my laboratory, Acoustic and Vibration Lab, by using a laser piston phone, a device that we developed specially for calibration of infrasound sensors, in part during the Infra-UV project. So one key point also here is that to provide an accurate comparison basis, we asked to the Static Pressure Lab to calibrate the barometer in a similar range, linear range, that the one used in infrasound. So typically only 10 or 20 Pascal. So we ask them to calibrate the sensor at plus minus 20 Pascal around the atmospheric pressure, which is approximately 1,000 hectopascal close to Paris. Okay, so here, now, this is not the figure. I apologize. I have normally another figure, so well, I will comment. The calibration, static calibration. So here are normally the result for the static pressure calibration. So the calibration cycle was performed with 2 Pascal steps, starting from the 1,000 hectopascal, after increasing of 20 Pascal, decreasing of 40 Pascals, and come back to the initial static pressure. So this simulates like a sinusoidal pattern, but of course here in DC. So this calibration leads to a sensitivity, which the linear regression leads to a sensitivity of minus 60.034 dB with an expected uncertainty of 0.056 dB in this case. So normally you have the output voltage as function of the input pressure, but this figure here is a measurement, measurement bias, which is a deviation between the measurement pressure after calibration from the reference pressure. So what's interesting here is that when following the calibration path, we can see like an hysteresis effect, but to be completely honest, at this stage of the study, it was not possible to conclude definitively if it's an effect of the sensor itself or from the calibration procedure. So the question stays open. Okay, here's the result for the dynamic method. So we used the laser piston phone. It was calibrated in the frequency range of 10 millihertz, 20 hertz. So you have the results here in amplitude and in phase. So as expected, the response, frequency response is relatively flat, with an average value for the sensitivity close to minus 60.04 dB, and the phase tends toward to 0 at low frequencies also as expected. And you can see here the typical uncertainties that we can reach with such a method. The larger uncertainties are achieved at the lower frequencies typically. Okay, so this slide is for the comparison between the static and dynamic results. So as a reminder here, you have the result for the static and dynamic with the uncertainties. So here the sensitivities are seems to in a good agreement within the uncertainties, but to check this more formally, we look for the normalized error. The normalized error is a classical performance criteria used to conclude on the consistency on bilateral comparisons. So the satisfactory range being that the normalized error must be below the unity to conclude to the consistency between the results. So you have here the normalized error as function of the frequency. And as you can see, all the values respect this, the normalized error are below, the unity, so that we can conclude on the consistency between the result of the static and the dynamic method. Just before to conclude, I just would like to discuss here probably an extra information regarding a potential limit on the static calibration. The fact is that calibrating a barometer with 2 Pascal steps over a 40 Pascal amplitude is very challenging. And this is not a classical, usual calibration service provided by the static pressure labs. The usual approach is instead to calibrate the barometer over its full range. This is why we obtain when we buy a new barometer, or if you ask for a usual calibration service, you will obtain this kind of result. So we did it here also. We asked to the static pressure lab to calibrate the same barometer but in the full range with a classical approach. So you can see here the black points reaching to a sensitivity of minus 59.998 dB, so slightly different than the one obtained previously, here the red data. So anyway, there is a small bias. It is covered by the uncertainty, so it is consistent, no problem, but just I would like to highlight here one fact is there is anyway a risk, specifically when the barometer is not perfectly linear, to have a bias or to underestimate the uncertainty with such approach, because finally, so some information is missing when provided such a classical calibration. Okay, it's time to conclude. So the key requirement for this study was to define a transfer standard covering the full infrasound range from the DC. As I said in the introductions, microphones play this role very well for high frequency, typically above 0.1 Hertz. And here the barometers can be seen as a promising candidate because the main advantage is we can use 2 calibration paths to calibrate them. So the static method provides very accurate results near to DC and ultra low frequencies, and the dynamic calibration methods becomes essential at higher frequencies when the response may deviate from the flat response, and it provides also the phase information, so this is important too. So finally, I believe that by combining these 2 complementary methods, probably with a smart combination, we could produce a more robust calibration and more robust working standard. For the next step, to be completely honest, my first intention was to present here other results for typically a Ch2 barometer, because it is a barometer which is very used also in the community, but I missed some time, so I apologize for that. But it could be a next step to extend this study to other barometers to strengthen consistency and robustness of this study. Thank you for your attention.
Thank you, Dominique. But are there any questions for Dominique from the audience? Darling, you have one. It's coming. Yeah.
Thank you for very interesting details on using the barometer. I think that certainly working proceeding.
It's not working.
This is better. Thank you for a very interesting talk, and I think it seems that the barometers have potential for something. However, I also have one, maybe it's a question. It looks like hysteresis on your going through the plus minus 20 Pascal. It looks like it didn't end the same place where you started. So that's my question, but I also have a few comments. That is 800 kilopascal, 880 kilopascal is not low enough. If you look at all the altitudes you can reach in the world, if you go around in mountains and things like that. So you need to know the dependence of
course.
altitude in the calibrations. And also I will say that we are working with microphones a lot, and they can go down to 10 millihertz. And I can say that I have an e-post on Thursday on that. Thanks.
Thank you, Erling. Any other questions for Dominique? I've got one comment. Very early in my career, I was asked whether we could prove that the static pressure Pascal was the same as the acoustic Pascal. And it seems like that's bothered me for a long time. We've not been able to demonstrate that until now, it seems. So do you think that's what you've shown through your measurements, that the static pressure Pascal and the acoustic Pascal are equivalent? Have you demonstrated that now?
I'm not sure I understood the question. Yeah,
So we have static pressure and sound pressure.
yeah.
Both are measured in pascals. Have you now demonstrated that the Pascal is the same for sound and for static?
I apologize, but the time was too short to present all the details. I specifically removed one slide to demonstrate that it was the same measurement.
Okay.
So, yeah, I can demonstrate it, but I remove it because it was the time was too short to present it. So
That's great. I might.
but we can
better now.
demonstrate, of course, yeah.
Thank you.
I can show you. But, thank you.
Okay, seems there are no more questions, so we'll move on to the last talk. Do you have the...
Thank you, Dominique.